My name is Mark Baumgartner. I'm from the Woods Hole Oceanographic Institution, and I'm going to be presenting evaluating the efficacy of real-time passive acoustic monitoring near offshore wind energy development activities to help mitigate risks to North Atlantic right whales. This work was funded by Equinor and the Huey W. Van Allen Clark Chair for Excellence in Oceanography. So when it comes to right whales and offshore wind development, our shared goals are to provide protections for North Atlantic right whales that enter risk zones where hearing damage from pile driving, noise exposure, or vessel strike in transit corridors are likely. There's a lot of interest in using real-time passive acoustic monitoring to detect and localize whales and trigger mitigation action, and this work really is about evaluating how effective passive acoustic monitoring can be for that purpose. Now, I have a paper on this in review at Endangered Species Research, and I looked at mitigating both behavioral disruption, hearing damage, as well as vessel strike risks associated with wind farm construction and operation. But for the purposes of this talk, I'm only going to focus on pile driving and level A harassment, that is permanent hearing damage. What you see on the right is sort of a conception of what a construction site would look like with a risk zone within which, if a whale got in there, it would be subject to permanent hearing damage. And then if we're localizing calls, a trigger zone in which, if a whale was localized in that, we might implement mitigation. And mitigation in this case, for the purposes of this talk, is going to be postponing pile driving. So I served on an expert panel to advise Equinor about the sort of universe of possibilities of monitoring techniques for right whales during pile driving operations. And I suddenly was faced with a lot of different questions about implementing real-time passive acoustic monitoring for mitigation, like how many PAM stations do we actually need? How far from the construction site should they be? Should we be localizing, or can we get away with just detecting whales and implementing mitigation based on detections only? If we do localize, how far away does a whale need to be localized before we trigger mitigation? And once we do trigger mitigation, how long should that mitigation last? Meaning, how long should we postpone pile driving? Faced with all of these questions, without a lot of sort of information to go on, one of the things that I like to do is to run simulations to try to get my arms around kind of complex problems like this. And so that was my strategy to answer these questions. So what I did was simulate a swimming, calling right whale in a confined domain for a long time and see how well each permutation of the number of PAM stations, station spacings, alerting methods, and mitigation rules perform in helping to mitigate interactions between the construction activity and right whales. If you're going to measure performance, you need some metrics, and these are the three metrics that I use. The first has to do with the protections for how well does the system protect right whales. And so that metric is how often does a whale enter the risk zone, but mitigation is not in place at that time. How often does a right whale either enter or is already there when pile driving commences? That's the probability of what I call the probability of missed mitigation, meaning you missed the fact that the whale was in the risk zone and you went ahead and started pile driving. The next two metrics have to do more with the cost to industry of the mitigation system. The first is how often is mitigation triggered, just in the simulations, what's the proportion of pile driving sessions that were postponed? And the third is how often is mitigation triggered, but the whale doesn't actually enter the risk zone. I call that the probability of false mitigation, or how many times did you say postpone, how many times did you postpone pile driving, and the whale that triggered that postponement doesn't actually show up in the risk zone. So with those metrics, we can choose which is the best PAM configuration, but how do we define best? So for the purposes of this study, I said that I wanted to use a maximum allowable probability of mismitigation to cull simulations that don't provide sufficient protection to right whales. I set that threshold at 0.15. That 0.15 assumes that there will be other monitoring modalities like visual observers on the platform, maybe infrared cameras, and so on. And then of the simulations that satisfy this threshold, of the simulations that provide the minimum level of protections for right whales, choose the one that costs industry the least. And that cost is going to be measured in the proportion of pile driving sessions postponed. But you could also consider the probability of false mitigation, the number of PAM stations, and the complexity of the learning method. Okay, so this is sort of a one slide to encapsulate all the methods of the simulation. So basically for the simulation, we trapped a swimming calling right whale in this 40 by 40 kilometer domain, having it swim around using swim speeds that are derived from the literature, swimming behavior that's derived from the literature, and then have that whale call. That's what the red dots are along the whale's track. Those are parameterized from Susan Park's work in terms of the interval between calling bouts. We'll also put in this domain a construction site with a risk zone around it. That's the dark gray circle. And then passive acoustic monitoring stations. Those are the 4 filled circles. We're going to, every time the whale makes a sound, we're going to see if that sound was detected on the PAM stations based on Hansen-Johnson's empirical detection function. And then if we're doing localization, if the whale is inside that trigger zone, then we'll implement mitigation. If we're not using localization, if the whale is just detected, we'll implement mitigation. So this was run 1,000 times. This was run for 10,000 days. That was one iteration of the simulation, and then we run the simulation 100 times for 100 iterations to get some variability in the metrics. For each simulation, we varied something in this list, either the number of PAM stations, the distance from the PAM stations from the construction site, the learning method, either detection only or localization, and then the mitigation rules as well, which are quite important. And then we'll use these metrics to determine which is the best. So the probability of missed mitigation, proportion of pile driving sessions postponed, and the probability of false mitigation. So I'm just going to jump to the results now. This is the results again, just for permanent hearing damage. We ran 255 simulations varying just those parameters that I just described. As you can see in the table with the results, you can see those parameters being varied. And then the last 3 columns are the 3 metrics that I described: probability of missed mitigation, false mitigation, the proportion of pile driving sessions postponed. Of the 255 simulations, 36 had a probability of missed mitigation less than 0.15, meaning 36 of these PAM station configurations provided sufficient protections based on this threshold. And what I'm showing you is that I then ordered those 36 by the proportion of pile driving sessions postponed, which is our measure of cost to industry, and I'm showing you the top 10. So these are the top 10, the cheapest or the least expensive to implement, okay, in terms of proportion of pile driving sessions postponed. So I'll just go through this table really quickly. The first thing that I want you to notice that all of the simulations had high probabilities of false mitigation. That is, when a whale is detected and you implement mitigation, it's very unlikely that that whale will actually end up in the risk zone. That's just a feature of using passive acoustic monitoring for this type of mitigation. In terms of costs, 17 to 32% of pile driving sessions were postponed. So about a quarter of all the pile driving sessions were postponed. If you're from industry, that might sound alarming, but I want to remind you that these simulations involve a whale that's only ever 40 kilometers away. We've trapped a whale within this 80 by 80 kilometer domain. And so a right whale is always nearby. So another way to say that is about 3/4 of pile driving sessions went on as scheduled when a right whale was actually nearby, which I actually think is not so bad, while still providing this minimum level of protections. If you want to do localization, great. There's no problem doing that. It's just you're going to need to use more PAM stations placed farther away from the construction site. Whereas if you use just detection only alerts, that requires fewer PAM stations placed closer to the construction site. So just to summarize, PAM systems can achieve good probabilities of miss mitigation with modest impact to pile driving operations when right whales are nearby with just a few PAM sensors and a detection-only alerting method. When combined with other monitoring modalities, PAM can be an effective contributor to an overall monitoring and mitigation system. But this requires regulators to think carefully about what these maximum allowable probability of miss mitigation should be for each of the risks. That's all I have. I want to thank the other members of the expert panel, Equinor's expert panel, for lots of great discussions, and I want to thank you for your attention.